order to improve our the way we teach. Okay, so today we are going to talk about the way to solve flowsheets first, and especially how to develop the resolution sequence. So if you remember, last week we have seen that there were several ways of solving a flowsheet, either using a simultaneous approach in which you write all the equations and then you have a mathematical tool that allows you to solve a set of nonlinear equations. This was one of the ways of solving the problem. The other way was to solve the problem in sequence, so it means that you solve one unit after the other one. And there was one remaining question there, is what is the best sequence? And what is the best sequence is something which I'm going to discuss now. But at the same time, we have also realized that if we need to solve a set of nonlinear equations, there is always one problematic, which is identifying what is the best initial guess for all the variables to guarantee that the Newton-Raphson procedure will converge, which also means that we can have tricks that allows us to identify what are the initial values that we have to use to start the procedure. And this would be also by solving sub-problems. That means that we can also define a sequence of problems that allows us to have a good value for the initial guess. And one of the examples that you will have to solve is the two-stage heat pump. The two-stage heat pump that has a list of units that you can see here. The list of units that are interconnected by strings. Okay. And the question is, what is the first unit that we have to solve? So if I'm asking you, let's try to solve the problems, where do you start? And there is a big silence because, in fact, it's impossible to decide where we start. Okay? We are in a system where we have loops and no way to decide where we start. So if we want to start here, well, I need the inlet conditions, and the inlet conditions are resulting from this calculation of this loop. So the idea would be to be able to identify where we have to start. So the principle that we have seen is that as soon as there is a loop, then there is a need to identify the streams that needs to be tiered, so cut. And for doing this, so the first thing we have to do is to draw the flow sheet. So this was the flow sheet. Now, what I'm going to do is that I'm going to give names. So on the one hand, we have the streams that I have here identified by numbers, and units that are identified by text. Okay? What is important here is that the streams defines what you would like to know. So you would like to be able to characterize the flows, the temperature, the pressures, the composition of each of those streams. And the units, MX1, L1, S1 here, are in fact the operators or the transformer of the states. Okay? If I have to define a sequence of resolution, what I have to do is that I have first to consider the shape of the models. And we can say that each unit is going to calculate the outlet if we know the inlet and the parameters that are in the unit. Which means that now we have to define the list or the order of the units that needs to be calculated. So when do I activate which model of which unit? Okay? And what we realize here is that, okay, we can, for example, start here. I know this unit here. And if I would know the 5 here, then I would be able to calculate the 3 by solving MX1. Knowing the 3, I would be able to calculate 4 by using R1. Knowing 4, and I would be able to calculate S by S1, I would be able to calculate the 5 and the 6. And knowing that the fact that I have the 5, then what I can do is that I can restart and go back to this unit here and verify that the 5 that I have calculated is equivalent to the 2 that I have here. So this is the principle of tiering, which is finally defining a solution sequence, because now what I can do is that I can guess the 2, solve mix 1 to obtain 3, solve L1 to obtain 4, solve S1 to obtain 5 and 6, test if 2 is equal to 5. If no, then I have to update the value, so I will have to make a loop here, okay, until I'm satisfied. And once I have I'm satisfied, then I can use the value of 6 to calculate by solving mix 2, I have to calculate 8. Okay, this is the principle of defining a sequence. So now I know what I have to do. I have to guess, I have to solve, I have to make a loop. Don't forget to test if if my loop is satisfied. If no, then update the value, and you know how to do this with an iterative procedure. And then afterwards, once the loop is solved, then I can go to the next step of the flow sheet. Okay, so the question is now, how do I define the ordered list of units and define the streams that can be calculated, which one will be calculated in the sequence? Okay, so now there is a special way of solving this problem. There is a special or a structured way to solve the problem. If I look at the, if I'm using the graph theorem, and what I'm going to explain you is how to solve even complex problems that allows to, how to define, the resolution sequence even for complex problems. And the principle is based on the following. So this was the reogram of the primary representation of my system. So I have the mix 1, L1, S1, and mix 2. And what I can see is that I have the streams 1, 3, 2, 4, 6, 7, and 8. Okay? So units are used to calculate the value of the streams. And what I can also say is that if I'm looking at this reogram, I can invert it, okay? Which is what we name the dual representation, which is going to say that 1 is coming from outside, so it is known. And if I'm applying mix 1, then I will be able to find the stream number 3, okay? But the stream number 3 is also needing the stream number 2 via the mix 1. So now I have 2 operators that allows me to calculate the stream number streams number 3, meaning that the stream number 3 has 2 anteriors or predecessors, which are the stream number 1 and the stream number 2. So you can see it here. Number 1 and number 2 are needed to calculate number 3. So this is the principle of the dual representation. I'm going to use this property in order to define the sequence. Something which is important to realize is that I'm talking here about units, okay? But I could also do it with equations, okay? Which is interesting because then it allows me also to use the same kind of tricks to identify the sequence of equation if I want to solve a set of equations in a sequential way. So the predecessors or the interiors can be seen from this diagram. And what the predecessors are telling me is who is needed in order to calculate the value of one stream. So what are the streams that are needed in order to calculate the value of a given stream? Okay, and what I will see here is also what are the operators, being units or being equations. Okay, so there is an algorithm that is named the Mottard algorithm that allows to define the sequence. And how does it work? First, what we can say is that if there is no interior left, it means that I know the stream. So if nothing is needed to calculate my value, then I know the value. Okay? It means also that if I need 2 to calculate 3, then each time I see only 2, I can replace 2 by 3. Okay? So this means that I can replace the interiors, the streams that have only one interior, by their interiors. And I will show you in a minute how it makes. But as soon as I do this, and if I have suppressed streams, so it means that now if 3 depends on 2 and 2 depends on 1, and 1 depends on nothing, so 1 is calculated, 1 is known, so it means that 2 is known, that means that 3 is known. Okay? So it means that I can go back and I can suppress the streams that have no interior if they have been replaced by something that is known. At a certain time, it will happen that the stream is depending on itself, meaning that I have identified a loop. If I identify a loop, then what I can do, I can tier it. I know that I have to guess this stream. So now I'm marking this stream as being tiered, and by tiering the stream makes it known. Okay, so it's like if I'm opening the loop and now the stream is entering the system. Okay, so meaning that I can go back to 1 because the tier stream is a stream that has no interior, so it can be replaced everywhere. Okay, and then I will continue like this. It might also happen that stream 1 is depending on 2 and 2 is depending on 1, so it will be the same principle. And it can also happen that 1 is depending on 2, 2 is depending on 3, and 3 is depending on 1. And then you will see that there will be also the possibility of tiering those 2 streams. Okay, so this is the Mottard algorithm, and what I'm going to do now is to show you how it works on different examples. Okay, so let's take this example here. So it's a process which has units here, a set of units, 3 loops. Okay, and the question is, where do what is the sequence to solve this problem? So I'm going to mark all the streams. Well, here is all the list of all the streams. And I'm going to look at who is needing who. So 1 is needing 0. 2 is needing 7, is needing 1, and is needing 5. 3 needs 2 and 4. 4 needs 3, 5 needs 3, 6 needs 3, 7 needs 6, 8 needs 6. Okay, so this is the principle of defining the anteriors or the predecessors. Okay? Now when I'm going to apply the Mottard algorithm, it means that I will identify, for example, that 0 is known. So it means that now each time I see 0, I can suppress it. Okay? And what I will see is that each time, so now this one has disappeared, so it means that each time I see 1, I can also suppress it because it is known. So, which means that, in fact, I'm starting by solving the unit 1, and now the system knows 1, in fact, and 0 is already calculated. So what I can see is that I can do it in this way. So I'm making the list, updating each time. So each time I'm seeing 0 here, I'm going to replace it by nothing, okay, because I know it. Which means, and then I can then see that the 1 has nothing, so it can also disappear, and I have a new list which is then given here. Now I'm going to continue the procedure, so each time I see 4 I can replace it by 3, each time I see 5 I can replace by 3, each time I see 6 I can replace by 3, each time I see 7 I can replace by 6, and each time I see 8 I can replace by 6. Okay, let's do it like this. So I'm going to, and of course, as I see, I have replaced by 6, and 6 can be replaced by 3. So I have finally this remaining list. which then means that I have replaced 4, 5, 6, 7, 8 by 3, and I have this new situation where 2 is depending on 3, 3 is depending on 2 and 3. Wow, now 3 is depending on 3. So what I know is that I have to guess 3. Okay, so I'm going to tier the 3, and therefore I'm over because as I know 3, there is nothing else to be guessed. Okay, so what does it mean? It means that if I'm guessing 3, so no, sorry. First, I will solve the unit 1 to calculate the string 2. The next step will be to guess 3 and solve unit 4. So I'm here, and I'm going to solve unit 4. So now I know 4, and I know 5. By solving unit 5, which is here, because now everything is known in the inlet of unit 5, I will calculate 7. Okay, knowing the stream 7, the stream 5, and realizing that I know already the stream 1 because I have calculated here, I will be able to calculate the stream 2. Okay? And when I know the stream 2 and I know the stream 4 that has been calculated here, I will be able to recalculate the stream 1, the stream 3. And once I have done this, now I have a new value for the stream 3. I'm going to loop. So I have now the 3 that is known here. I will make the loop, test if the guess was correct. If not, give a new value and resolve the sequence. So again, I'm showing you the sequence. So before starting the loop, I'm solving unit 1, so that I know 1. Then I'm guessing the string number 3, which is here. I'm going to solve unit 4. With the unit 4, I'm going to calculate 4 and 5 and 6. Knowing 6, I can calculate 5. I'm going to have the stream 7, and I know this one, and I know this one, so I can calculate, by solving the unit 2, I can calculate the stream 2. Knowing the 4 and the 2, I will be able to recalculate 3, and I'm going to make a loop. So just by tiering this string here, I'm able to solve the whole sequence. Okay? So it's a systematic method. It's a systematic method that allows me to define the solving sequence, which then allows me to know what needs to be done. And when I have solved the stream 3, I still have to calculate the unit 6, but it is known because now, after having converged the tree, the value of 8 is known, and by solving the unit 6, I can then obtain the value of 9. Okay? So what I have identified here is a sequence that allows me to make the calculation about the list of units in an ordered way to be solved, that allows to identify which one of the stream needs to be tiered, so for which I have to make a guess of the value, and that will create a loop and an iterative process in such a way that I will at the end be able to calculate the whole system. Now the tiering can be done in different ways. One way is it might happen that the only value that you need is the mass flow. Sometimes the conditions are known, but the mass flow is unknown. Okay. In other situations, it will be the mass flow is easy to obtain, but the temperature and pressures are unknown, so you will not only guess the temperature and pressure, or you can guess the whole list of variables: mass flows, temperature, pressures, and composition. Okay. So this is a typical case, but when you understand what is the list of equations, sometimes it's possible to make the process easier to solve the tiering equations. Now, the tiering equations can be of two types. So if you are solving the problem as in a sequence, so typically you will use a substitution mechanism. which means that you recalculate the value at iteration k, and you obtain the new value at the end of the sequence that you can then re-inject in the loop. Okay? But don't forget to test if the new value is different from the previous one. Otherwise, because you have to be sure that the loop is going to converge. And of course, instead of using this mechanism of substitution, you can always solve the equation and use typical methods to solve a set of non-linear equations. I'm saying a set of non-linear equations because it might happen that instead of having only one variable here, you will have in the xk the temperature, the pressure, the composition, and the flow. Okay, so it means that it's a set of non-linear equations.